Hey everyone, welcome back to CodeHub Pro. In the previous video, we talked about the Internet Protocol, but now let's better understand what the Internet is, network types, topology, devices, OSI Model and TCP IP model. Let's get started. The Internet is a global network connecting millions of private, public, academic, business, and government networks. It allows for the exchange of information and communication through various interconnected devices. Types of Internet connections: dial-up, uses a phone line for connection, very slow compared to modern standards. DSL, digital subscriber line, uses phone lines but offers higher speeds than dial-up. Cable, uses cable TV lines to provide high-speed Internet access. Fiber optic, uses light to transmit data, offering extremely high speeds. Satellite, uses satellites to provide Internet access in remote areas. Wireless, Wi-Fi, uses radio waves to provide Internet access to devices within a certain range. Now let's talk about network types. The most widely spread network types are Network Types Personal Area Network, PAN, a tiny personal network like your smartphone connecting to wireless earbuds within a short range. Local Area Network, LAN, connects computers and devices within a building or small area, used to share resources like files and printers. Metropolitan Area Network, MAN, covers a city or large campus area, typically using high-speed fiber optics. Wide Area Network, WAN, spans over large geographical distances, connecting LANs and MANs globally. Special network types, Wireless LAN Network, WLAN, similar to LAN but wireless, using radio waves for connectivity. Virtual Private Network, VPN, provides secure private communication over a public network like the Internet. Let's start our network tour with the smallest network, Personal Area Network, PAN. What is PAN? A PAN is a tiny personal network. Think of your smartphone, smartwatch, and wireless earbuds all connecting within a short range. When do we use PAN? PANs are great for connecting personal devices around you, usually within about 10 meters. Examples include using Bluetooth to connect your phone to a speaker or using a wireless mouse and keyboard with your laptop. Next up is the Local Area Network, LAN. LANs are super common and are used in homes, offices, and schools. A LAN connects computers and other devices within a building or a small area. When do we use LAN? We use LANs to share resources like files, printers, and Internet connections within a confined area. If you're in an office or school where all computers are networked together, that's a LAN in action. Moving up in size, we have the Metropolitan Area Network, MAN. A MAN covers a larger area like a city or a large campus. It's bigger than a LAN, but smaller than a WAN. MANs are used to connect multiple LANs within a city or town. For instance, a university might use a MAN to link different campus buildings. Your city's cable TV network or municipal Wi-Fi could also be examples of a MAN. The biggest one is the Wide Area Network, WAN. WANs connect devices over vast distances, even across countries and continents. The Internet is the largest and most well-known WAN. WANs are used when you need to communicate over long distances. Businesses use WANs to connect their offices worldwide, and you use a WAN whenever you access the Internet. Now let's talk about the special types of networks. Wireless LAN, WLAN. A WLAN is just like a LAN but without the cables. It uses Wi-Fi to connect devices. When do we use WLAN? We use WLANs when we need the flexibility to move around. At home, you connect your devices to a Wi-Fi router to access the Internet without being tethered by cables. Virtual Private Network, VPN. What is VPN? A VPN creates a secure connection over a less secure network, like the Internet. It's like having a private tunnel for your data. When do we use VPN? We use VPNs to protect our privacy and secure our Internet connection. They're essential for safely accessing remote networks, like working from home and connecting to your office network, or for safely browsing the Internet on public Wi-Fi. Understanding these network types helps you see how our world stays connected. From your personal gadgets to the vast Internet, each network type plays a crucial role in our daily lives. Now, let's talk about network topologies. Let's break it down in a simple and friendly way. Network topology refers to the arrangement of different elements, links, nodes, etc., in a computer network. There are several types of network topologies, each with its own strengths and weaknesses. The most common ones are bus, star, ring, mesh, and hybrid topologies. First, let's talk about the bus topology. What is bus topology? In a bus topology, all devices are connected to a single central cable known as the bus or backbone. Bus topology is simple and cost-effective, ideal for small networks or temporary setups. However, it's not suitable for large networks because if the central cable fails, the whole network goes down. Next up is the star topology. In a star topology, all devices are connected to a central hub or switch. The hub acts as a repeater for data flow. Star topology is popular in home and office networks because it's easy to manage and expand. If one device or cable fails, it doesn't affect the rest of the network. However, if the central hub fails, the entire network goes down. Now let's look at the ring topology. In a ring topology, each device is connected to two other devices, forming a circular pathway for signals. Ring topology can perform well in networks with high traffic because data travels in one direction, reducing the chances of packet collisions. However, if one device or cable fails, it can disrupt the entire network. Moving on to the mesh topology. In a mesh topology, every device is connected to every other device in the network. There are two types: full mesh, where every device is connected to every other device, and partial mesh, where some devices are connected to all the others, and some are connected to only those with which they exchange the most data. Mesh topology is highly reliable and offers redundancy because there are multiple paths for data to travel. It's commonly used in large and critical networks like those of the Internet. The downside is it's expensive and complex to install and manage. Lastly, we have the hybrid topology. What is hybrid topology? Hybrid topology is a combination of two or more different types of topologies. It takes advantage of the strengths of each individual topology. When do we use hybrid topology? Hybrid topology is flexible and scalable, making it suitable for large, complex networks like those in enterprises and data centers. It can be tailored to meet specific network requirements, but can be complex and costly to implement. Understanding these network topologies helps you design networks that are efficient, reliable, and meet your specific needs. Whether you're setting up a home network or designing a large enterprise network, choosing the right topology is crucial. What is network devices? Network devices are the hardware components that connect computers and other electronic devices together to form a network. Some of the most common network devices include routers, switches, hubs, modems, access points, and firewalls. First, let's talk about routers. A router is a device that forwards data packets between computer networks. It directs traffic on the Internet. Routers are used in homes and businesses to connect local networks to the Internet. They ensure that data gets sent to the correct destination, whether it's within your local network or across the Internet. Next up is the switch. A switch is a device that connects multiple devices within a local network and uses MAC addresses to forward data to the correct device. Switches are used to expand networks and improve performance by ensuring that data only goes where it's needed. This makes them ideal for larger networks with lots of devices, like in offices and data centers. Now, let's look at the hub. A hub is a basic device that connects multiple Ethernet devices, making them act as a single network segment. Hubs are used in small networks where simplicity and low cost are priorities. However, because they broadcast data to all devices on the network, they are less efficient and secure than switches. Moving on to the modem. A modem, modulator-demodulator, is a device that converts digital data from a computer into a format suitable for a transmission medium and vice versa. When do we use a modem? Modems are used to connect your home network to your Internet Service Provider, ISP. They convert the digital data from your devices into signals that can be sent over phone lines, cable systems, or satellite links. Next is the access point. An access point is a device that allows wireless devices to connect to a wired network using Wi-Fi. Access points are used to extend the range and coverage of a wireless network. They are ideal for large homes, offices, or public places where you need Wi-Fi access in multiple locations. Finally, let's talk about firewalls. What is a firewall? A firewall is a security device that monitors and controls incoming and outgoing network traffic based on predetermined security rules. Firewalls are used to protect networks from unauthorized access and cyber threats. They are essential for both home and business networks to safeguard sensitive data and prevent malicious attacks. Understanding these network devices helps you build and maintain efficient and secure networks. Whether you're setting up a home network or managing a large enterprise network, knowing what each device does and when to use it is crucial. Now, let's talk about OSI Model. We'll look at what it is, the layers it consists of, and the functions each layer performs. We'll also cover encapsulation, protocols, and see an example of how data flows through all the layers. Why do we need the OSI model? In the modern technological landscape, countless devices from various manufacturers coexist. These include network devices, peripheral devices, processors, motherboards, and more. The need for these diverse devices to communicate seamlessly is critical for transmitting information. However, this necessity introduces challenges related to device compatibility and selection. Each manufacturer employs unique methods for information processing, and while some methods become standard in certain fields, the same operation might be handled differently by different manufacturers, leading to complications in data transfer. For example, transferring data between network equipment from different manufacturers can be both challenging and time-consuming. Moreover, different operating systems like Android and Windows come with their own sets of features, architectures, and file systems. Consider the task of transferring a file from an Android device to a Windows-based device. What methods and functions should be employed for data transmission over a network? Additionally, the types of data being transmitted, whether text, audio, or video, must be accurately identified and transmitted without errors or delays to ensure data integrity. To address these issues, a unified data transfer model known as the OSI, Open System Interconnection Model, was created. Alongside this model, standardized data transmission protocols were established to ensure compatibility and efficient communication across diverse devices and systems. What is a protocol? A protocol is akin to a language for devices. Just as it's challenging to solve a problem with someone if you don't speak their language, devices require common principles and standards to interact effectively. A protocol is a set of rules that describes how devices communicate on a network, ensuring smooth and efficient data transfer. What is the OSI model? The OSI model is a reference framework that standardizes network communication between two endpoints in a network. This model allows different devices to interact with one another seamlessly. Developed by the International Organization for Standardization, ISO, from 1977 to 1984, the OSI model divides the communication process into 7 simpler, distinct layers. 1. Physical layer. 2. Data link layer. 3. Network layer. 4. Transport layer. 5. Session layer. 6. Presentation layer. 7. Application layer. Each layer performs specific functions, and any protocol within the OSI model must interact with protocols at its layer or with those one layer above or below it. This interaction can be horizontal, within the same layer, or vertical, between layers. Encapsulation. Encapsulation in networking is the process of adding additional information, usually protocol headers, to data to prepare it for transmission. Each layer of the OSI model adds its own information to the data, and the receiving party performs decapsulation. During decapsulation, the protocol headers are read and removed, and the data is passed up the layers until it's fully restored to its original form. For example, the third layer, network layer, deals with packets, while the fourth layer, transport layer, deals with segments or datagrams. The process of encapsulation and decapsulation ensures that data is correctly transmitted and received, maintaining its integrity and coherence. The layers of the OSI Model 1. Application layer, Layer 7. Function. This layer allows user applications to interact with the network. It provides protocols and interfaces that enable software applications to request and deliver network services. Examples: HTTP, Hypertext Transfer Protocol; HTTPS, Hypertext Transfer Protocol Secure; FTP, File Transfer Protocol; Telnet. 2. Presentation layer, Layer 6. Function. This layer is responsible for data translation, encryption, and compression. It ensures that the data sent from the application layer of one system is readable by the application layer of another system. Examples: SSL, Secure Sockets Layer; TLS, Transport Layer Security; JPEG, Joint Photographic Experts Group; MPEG, Moving Picture Experts Group. 3. Session layer, Layer 5. Function. The session layer manages and controls the connections between computers. It establishes, manages, and terminates sessions between two communicating hosts. Examples: NetBIOS, Network Basic Input-Output System; PAP, Password Authentication Protocol; RPC, Remote Procedure Call; PPTP, Point-to-Point Tunneling Protocol. 4. Transport layer, Layer 4. Function. This layer provides reliable data transfer services to the upper layers. It is responsible for end-to-end communication, error detection, and flow control. Examples: TCP, Transmission Control Protocol, which guarantees delivery; UDP, User Datagram Protocol, which does not guarantee delivery. 5. Network layer, Layer 3. Function. The network layer manages data routing and logical addressing. It determines the best path for data transfer and handles packet forwarding, including routing through intermediate routers. Examples: IP, Internet Protocol; ICMP, Internet Control Message Protocol; IGMP, Internet Group Management Protocol. 6. Data link layer, Layer 2. Function. This layer handles error detection and correction as well as framing. It is responsible for MAC, Media Access Control, addressing, and provides a reliable link between two directly connected nodes. Examples: Ethernet, ARP, Address Resolution Protocol; MPLS, Multi-Protocol Label Switching. 7. Physical layer, Layer 1. Function. The physical layer is responsible for transmitting raw bit streams over physical media, such as cables and wireless signals. It defines the hardware elements involved, including cables, switches, and NIC, Network Interface Card. Examples: hubs, repeaters, media converters. Data flow through the OSI model. Data transmission starts at the top, application layer, and goes down through each layer, where it's encapsulated with the necessary protocol information. Once the data reaches the physical layer, it is transmitted over the network. On the receiving end, the data travels up through each layer, where it's decapsulated and processed, ensuring that the original data is correctly received and understood. Understanding the OSI model is crucial for ensuring smooth and efficient network communication. It standardizes interactions, facilitating compatibility between different devices and systems, and ensures that data integrity is maintained during transmission. In this section, we'll explore the TCP/IP model, delving into its history, examining its layers and their functions, and comparing it to the OSI model. We'll also discuss the hybrid 5-layer TCP/IP model and provide a detailed example of how data passes through all layers of this model. History of TCP/IP. In 1968, the U.S. Department of Defense anticipated the need for a reliable information transmission system in case of war. This foresight led to the development of ARPANET by the Defense Advanced Research Projects Agency, DARPA, which served as the precursor to today's Internet. In 1974, the Transmission Control Protocol, TCP, was developed to manage data transfer and routing within ARPANET. As ARPANET expanded, the responsibilities of the TCP protocol were split into two separate protocols: TCP, Transmission Control Protocol, and IP, Internet Protocol. This division laid the foundation for the TCP/IP model. First formally standardized in September 1981, the TCP/IP model became the foundational protocol suite for computer networking and the Internet. It consists of 4 layers. 1. Application layer. This layer provides network services directly to applications. Protocols include HTTP, HTTPS, FTP, SMTP, and more. This layer interacts directly with software applications, enabling user-oriented services. 2. Transport layer, responsible for end-to-end communication between hosts. TCP provides reliable, connection-oriented communication, e.g., for web browsing, while UDP offers unreliable, connectionless communication, e.g., for real-time applications like video streaming. 3. Internet layer handles the addressing, routing, and packaging of data packets across networks. The Internet Protocol, IP, is the core protocol here, defining how data is routed between devices across different networks. 4. Link layer, also known as the network interface layer. This layer defines how data is formatted for transmission over the physical medium, e.g., Ethernet, Wi-Fi. It deals with physical addressing, MAC addresses, and error detection. Comparing TCP, IP, and OSI models. The TCP/IP model differs from the OSI, Open Systems Interconnection model, which has 7 layers. Here are some key differences. Layer count. OSI has 7 layers, while TCP/IP has 4. Functionality. TCP/IP combines several OSI layers into its fewer layers, simplifying networking concepts. Scope. The OSI model is more of a theoretical framework, while TCP/IP is practical and widely used, especially in Internet communications. Hybrid 5-layer TCP/IP model. A hybrid approach, sometimes referred to as a 5-layer TCP/IP model, includes physical layer, deals with the transmission medium, cables, wireless signals. Data link layer, controls data flow over the physical medium. Network layer, routes data packets between networks, IP addresses. Transport layer, provides end-to-end communication, TCP, UDP. Application layer, supports network applications, HTTP, FTP. Data transmission in the TCP/IP model. Consider an example of data transmission using HTTP in a simplified 5-layer TCP/IP model. 1. Application layer. User action. The user enters a URL, e.g. not www.example.com, into their web browser. HTTP request. The browser creates an HTTP GET request to retrieve the web page. DNS query. The browser may also initiate a DNS query to resolve the domain name www.example.com to an IP address. 2. Transport layer. TCP segment. The HTTP request is encapsulated into a TCP segment. The TCP segment includes a source port and a destination port, typically port 80 for HTTP. Connection establishment. TCP initiates a 3-way handshake with the server to establish a connection. This involves sending a SYN, synchronized packet, receiving a SYN ACK, synchronize acknowledge packet from the server, and replying with an ACK, acknowledge packet. 3. Internet layer. IP packet. The TCP segment is encapsulated into an IP packet. The IP packet includes the source IP address, the user's device, and the destination IP address, the web server. Routing. The IP packet is routed through various network devices, routers, to reach the destination IP address. 4. Data link layer. Ethernet frame. The IP packet is encapsulated into an Ethernet frame. The Ethernet frame includes the source MAC address, the user's network interface card, and the destination MAC address, the next hop, which could be the user's router or an intermediary device. Local delivery. The Ethernet frame is delivered to the next hop in the network, and this process repeats until the frame reaches the final destination, the web server's network interface. 5. Physical layer. Transmission. The Ethernet frame's bits are transmitted over the physical medium, e.g., copper wire, fiber optic cable, or wireless signal, to the next hop. On the server side, 1. Physical layer. The server receives the bits over its network interface and reconstructs the Ethernet frame. 2. Data link layer. The server decapsulates the Ethernet frame to retrieve the IP packet. 3. Internet layer. The server decapsulates the IP packet to retrieve the TCP segment. 4. Transport layer. The server processes the TCP segment, acknowledging receipt and reassembling any fragmented segments. 5. Application layer. The server processes the HTTP request, retrieves the requested web page, and sends an HTTP response back to the client through the same process in reverse order. Conclusion. The TCP/IP model is the foundation of modern networking and the Internet. It provides a standardized approach to data transmission across diverse networks, ensuring compatibility and efficient communication between different devices and systems. Its simplicity and efficiency have made it indispensable in the digital age, supporting everything from web browsing to global communications. In this video, we explored Internet, network types, topologies, devices, OSI model, and TCP/IP model in detail, understanding their layers, functions, and how they facilitate seamless network communication. I hope this comprehensive explanation has helped you grasp these fundamental networking concepts better. If you found this video informative, please consider liking it, leaving a comment, and subscribing to my channel, CodeHub Pro, for more insightful content like this. Your support means a lot. Stay tuned for our next video, where we'll continue exploring essential networking topics. See you next time on CodeHub Pro.